Okay, so now I'm recording this lecture. So let's start. So as I mentioned, I will finish chapter 4, and then probably today I will start chapter 5, and then Tuesday we will also continue chapter 5, and on Friday we will have a comprehensive review session. Okay, so let's continue chapter 4. Chapter 4 is mostly electrostatic. So we continue the chapter 4. Which is mostly electric field under steady state conditions. So we have defined the Poisson's equations, okay? The Jacobian of the voltage is equal to the minus to the volume charge density divided by the permittivity. And we also, in case this is the Poisson's equations, and in case there is no, or the total charge inside, for example, the conductor is 0, then we just obtain Laplace equation. So Laplace equations is this one. Okay. Now we will go to the conductors. We'll talk a little bit about conductors. So we already started last time. So a conductor is a material that conducts electricity, where there is a little resistance to electric field, to the electric current, to the motion of current, and we know that the current density is equal to the conductivity times the electric field. And we also define. So let's say if I have okay, just yeah, so I want to just close my email so that I don't get notifications. Okay, so if I have, let's say, a cable, this is a cable, and I apply, for example, an electric field, so the electrons will start moving with the velocity that we will call the drift velocity. So this is the drift velocity, and the electrons will start moving. There is a quantity that gives the relationship between the velocity of the electrons, or the drift velocity of the electrons and the electric field. This quantity is called the mobility. So the mobility is equal to the drift velocity, or let me put it in a correct way. So the drift velocity is equal to the with a minus sign, because you know the mobility is a positive constant, and the drift velocity of the electrons is always in the opposite direction of the electric field. Or you can go to the magnitude, and then it will be this. Okay. We also derived the fact that the density, the current density, is equal to the volume charge density times the drift velocity. So this is the volume charge density. Okay. And we also we talk about the number of free electrons per volume. This is the number of electrons that can move per volume, and the conductivity can also be expressed as the number of electrons times the mobility of electrons and times the charge of electrons. Okay? So this is the number of electrons, the mobility, and the electric charge, which is 1.610 to the minus 19 coulomb. Now, this is only for conductors. In here, I'm not covering semiconductors, even though in the textbook there is one section, small section about semiconductors, because I believe semiconductors, we will cover them. For those who are doing physics 322, we will cover them in detail, and also we'll cover them next spring in 317. Okay. Any question? I'm just reviewing what we have done. We also defined the Joule's law. So Joule's law is the law about the power. Now, Joule's law, we can write it as, in general, you can look at the textbook, but the power, so this is the power. We know that the power is the rate of change of energy. Okay, the power is the rate of change of the energy, how much energy is consumed per time. Okay, now we can easily see that the power can be defined as the dot product of the electric field, the density, the current density, the integral over the volume. Okay, this is the integral over the volume. And you can also, we know that J is equal to sigma E, which means we can also get it is equal to, if I replace J by its value, it will be equal to sigma, and of course the magnitude of this. Okay, so this is the definition of the power. Now let's see, if you remember, we have a common, an easy equation that we defined when the electric field is constant, when the voltage is constant, with the current constant. This we have done in physics 2, in electricity. Let's retrieve it here. Let's assume in the case of a resistor, this is a general equation, but in case of a resistor, okay, let's say in case of resistor, we have this is the length, this is the area, okay, and the power will be equal to sigma times the E square, the volume. Volume is, let's say, dLA. Okay? If I integrate, because those are constant, if I integrate, it will be sigma E square L A. Now, what is this? I can also put sigma EA, well, and then E times L. What is E times L? So this is the electric field. The electric field times L is what? Which quantity, if I multiply the electric field applied to a cable as a function and multiply it by its length, it gives me which quantity? Hello? Any idea? How do you apply electric field? How do you apply electric field to this copper cable? If I want to apply an electric field. Exactly. So you apply potential difference, yeah. So, and the potential difference, yeah. So the electric field is equal to delta V over the length. Yeah. So this quantity is delta V, is the voltage. Okay. And what is this quantity? Who can tell me what is this quantity? Well, I know that sigma, okay, E times A, I know that this is equal to the current density. The current density times A, it gives me which quantity? Current density times the area. It gives me which quantity? Exactly, the current. Yeah, the current. So this is the current. And you can see the power is equal to I times the voltage. This is the, if you remember, this is the equation that we saw in physics 2. Because we had electric current that is constant and the potential difference is constant, and the resistor has constant fixed dimensions. But the general formula are those ones. If you have, we'll see it in transient circuit, we will use these quantities as the definition of the power. Okay. Any question? Okay. So this is for the conductors. For the conductors, we defined the conductivity, the mobility of electrons, the drift velocity of electrons, of course, the electric field that is applied. We also define the current density, the current, and the power. Okay, those are quantities that define a conductor, or that are intrinsic to a conductor. Some of them are intrinsic, like the conductivity. Conductivity is specific to a conductor, and others are related to properties, geometrical properties, and also the potential difference that is applied to the conductor. Okay. So now let's go to another material, which are the dielectrics. In fact, what are we trying to do here? Let me open another page just to remind you or give you what we are trying to do. This chapter is about electrostatics. Electrostatics. Just to remind you what we are trying to do. Electrostatics is when you have the electric field, the change of the electric field as a function of time is zero. So the electric field does not change as a function of time. It can change as a function of the distance, the position, but not as a function of time. So what we are trying to see, we are trying to calculate, so what happens to the properties of a conductor and what happens to the properties of a dielectric, okay, under these conditions, okay, and then not only that, but what happens when I have a material where I have to put in contact conductor or conductor dielectric or dielectric, and so on. So what will happen under these conditions? So this is what we will call the boundary conditions. So this is exactly what is this chapter about. So now let's calculate. Let's see what is the dielectric. Dielectric. In fact, in a conductor, electrons are always at the outer shell. The electrons that are at the outer shell are weakly bounded. So that's why it's easy when you apply an electric field, those electrons will move easily in the case of a conductor. Okay? In the case of a dielectric, those electrons are strongly bounded. And that's why it is extremely difficult to produce a current, almost impossible to produce a current using dielectric, just because those electrons, they are strongly bounded to the atom. Even if you apply potential difference, they will not move. Okay. So this is the main difference, and we have seen this in physics too. Now let's give a very small drawing about the what we call polarization. Polarization in a dielectric. In fact, let's assume I have this is a dielectric, and so the dielectrics, the charges are randomly distributed. However, if I apply a potential difference, this is a dielectric. If I apply a potential difference, what happens is that the positive charges will move this side and the negative charges will move this side. Well, this means that I have now introduced an internal electric field that is called polarization. Remember, the electric field goes from the positive potential or from the largest potential to the smallest potential. So this is called the polarization field, polarization electric field. So it's called the polarization electric field. The polarization is always smaller than the electric field. So it is, in magnitude, the polarization is smaller than the electric field, and it is in opposite direction. So they are in opposite direction. It's always in opposite direction. Okay. So let's see derive an equation for the polarization field. For this polarization field, we know that in free space, the density is given, or the density, the electric flux density is equal to the permittivity of free space times the electric field. Okay. Now, in the presence of dielectric polarization, or dielectric polarization. So we have, in addition to that, we have a polarization field that is added to the total field, of course, because the total will be the vectorial sum of the two fields. Okay, so let's first define the following. A dielectric is said to be linear if the polarization field is proportional to the external electric field. Proportional. Okay, so this is one definition. A dielectric is also called isotropic if the polarization and the polarization field and the electric field have the same direction. Same direction means parallel. They are anti-parallel. They will not have the same direction, but they are in the same, anti-parallel to each other. A dielectric is also called homogeneous. Homogeneous if the permittivity and the permeability and the conductivity are constant throughout the medium. Okay, so those are three definitions of sort or common types of dielectrics. So in this course, we'll consider a dielectric that has three properties. So we'll just limit ourselves that the dielectrics that are linear, isotropic, and homogeneous. Okay. So in this case, the polarization field can be written as the free space permittivity times a constant times the electric field. Okay, so this constant is called electric susceptibility. Electric susceptibility. In this case, if I look at the total flux density, which is equal to epsilon 0 E, plus the polarization field, which is epsilon 0 E, this gives me the epsilon 0 1 plus this. Yes. Okay, and this is called the permittivity of the dielectric. So the permittivity of the dielectric is equal to the permittivity of free space times 1 plus the electric susceptibility. Okay, so we are able to do this because we are, if you remember, it's a linear. Linear means that the polarization field is proportional to the electric field. And this proportionality factor is called the susceptibility of the electric susceptibility. Any question? Any question? So just tell me, do you want me to give you the chance to copy, or if I'm going fast, just tell me so that I slow down a little bit. If you are copying, just tell me to stop a little bit so that you can copy. Okay. Okay. Yeah. Okay. Okay. So another thing is the dielectric breakdown. Again, you have seen this, but I will not go into the detail. I just want to mention here that dielectric should not be subject to large electric field. So if you apply a very, very large electric field to a dielectric, there will be a phenomenon called breakdown, where some of the electrons will still be able to be extracted from the molecules or from the atoms, and they will induce a kind of short circuit, which will make your dielectric somehow conductor, and then it will just lead to a breakdown. This is what you do, for example, when you have a capacitor. This is a capacitor, you have a positive, for example, negative, and you have a dielectric here, right? So now, if you apply a very, very high voltage to your to the capacitor, what happens is that this dielectric will start having electrons extracted, and this means it's like if you are creating a short circuit between the positive and negative charge, and then your capacitor blows up. Okay, so the dielectric breakdown is when you apply a large electric field, can lead to a dielectric breakdown. And in fact, each dielectric has what we call a value of the electric field that should not be exceeded. So the dielectric strength called EDS is the maximum, I will call it the maximum electric field value that must not be exceeded, or that cannot not be exceeded. Okay, so a dielectric so dielectric strength is an electric field value for each dielectric that should not be exceeded. If you exceed this value, the dielectric will go to a breakdown, because then you are so you are breaking this bond between the external electrons and the atom itself, and then you start extracting electrons from this dielectric, which is not good. Any question? Okay. Now we'll go to an interesting application, which is the electric boundary conditions. This is very important. So the electric boundary conditions. Now, let me do something. Why are we interested in those electric boundary conditions? Just to explain a little bit. Electric boundary conditions are used when you are trying to calculate the electric field in a material that is composed of different materials, like a dielectric, conductor, etc. Let's assume in our application, for example, let's assume you are building a detector, for example. So I'm building a detector, or let's say I am building a capacitor, very large capacitor. What is a capacitor? Capacitor has conductor. This is a conductor. This is another conductor, right? And this is a dielectric, right? This is a dielectric. Now, what is interesting for me, I can easily calculate the electric field here inside. Of course, the electric field here, I will talk about it later. But what is very, very interesting and very important for the work that I will be doing, and the simulation I will be doing, the application I will be doing, what happens in the boundary? What happens to the electric field in the boundaries of this? So I must find, I know there is an electric field here, I will call it E1, and I know that there is an electric field here, E2, but can I find the electric field exactly at the boundaries if I know E1 and E2? Because this is very important, at the boundaries. You can also have something like that. This is a capacitor, here you have a conductor, here you have another conductor, even another type, conductor number 1, conductor number 2, not the same. And in many applications, we have different dielectric. I have dielectric number 1, and I have dielectric number 2. So here it's even worse, because this is a contact between a conductor number 1 and dielectric number 1. Here I have a contact between two dielectrics that are completely different. And here I have conductor between dielectric 2 and conductor number 2. I need to understand, based on the material properties and on the electric field inside each material, how can I calculate the boundaries? Because this is very important. If you miss the boundaries, you get some divergent solution or nonsense solution. So this is what we are trying to do, because this is very important. Any question? So that's why we want to calculate the boundary conditions. So the goal here is, I will call them BC, which is the boundary conditions. We want to calculate, to derive a set of equations, that these equations will enable me to calculate the electric field, the density, the electric field density, the current density at the interface between two media. And believe me, one of the big problems, actually, we are running some simulation for our detectors using some new software. And I can tell you one of the big problems that my postdoc is struggling now with is that this software is not giving a good estimation or calculation of the boundaries between two metals and two dielectrics. And we are trying to figure out what is wrong with this software, because it gives us completely different results than what we see in experimental measurement. Okay. Now, of course, those boundary conditions will be calculated in electrostatic conditions. Okay, who can remind me what is electrostatic condition? Wait. Who can remind me what is electrostatic condition? Are you following? What is electrostatic condition? Exactly. When there is no change, very good. Nor. So yes, electrostatic conditions when there is no dependence on time of the electric field. So we will calculate them under electrostatic conditions, and later you will see in chapter 7 and 8, we will extend our calculation to electric field and magnetic field that depend on time. Okay, so let's do the first thing. Take any two materials, I need you to follow with me, please, here. Yeah, I will start. So now I'm calculating the boundary conditions. Let's take two materials. So this is material number 1, and this is material number 2, and here in black is the boundary between them. Material number 1 has permittivity epsilon 1. Material number 2 has permittivity number 2, and there is an electric field inside material number 1, and there is an electric field inside number 2. So what we are trying to do, we know that E1 has a component along the x-axis. We call it tangential component and normal component. E1 tangential and E1 normal. The same thing, E2. So E2 has, this is E2, has tangential. Tangential means tangent to the interface. So this is the interface between the two materials and normal, E2 normal. And the question here is, so the E1 has a tangential and normal. E2 has, again, also tangential and normal. So what happens to those tangential and normal component when we cross the borders? So for that, let's take the property of the conservation of electric field. Electric field is conservative. For that, let's take the following. Let's take this. Should I use another color? Yes, use another color. Let's take this. Okay, this rectangle, and this rectangle, I will call it A, B, D, D, and C. So this I will solve analytically, just to show you how do we do this, and then we can solve the others directly. So, but for the moment, I will show you step by step what we do here. Now we know that the electric field is conservative, conservation property or conservation property. Property of the electric field. So what is the conservation property of the electric field? Is the fact the integral over A, B, C, D, the whole loop of the electric field, E dl, is equal to 0. This is a conservation property, right? Now, let's apply it here. This means that the integral from A to B plus the integral from B to D, from the integral plus D to C, plus the integral from C to A is equal to 0. Now, we will, since we are doing the interface, we can make this A and C very, very, very small, a very thin layer, so that it's almost 0. This one will go. So we just squeeze the width, because we are looking at just the interface. So those two parts will not contribute, because we are minimizing them to almost a line just at the interface. So we are getting the integral from A to B. So the integral from A to B of E dl plus the integral from D to C of E. Now remember, the integral from A to B, this is E1, dl1, because the A and B, the segment AB is in medium number 1, and segment DC is in medium number 2. So that's why I am doing this here. And you can easily see that what is E1 dl1? D1 dl1 is the normal, the tangential 1 times L1, the length. L1 is this, well, this one. And what is E2 dl2? This is tangential 2 times L2 with a minus sign, because they are in opposite direction. So this is E1 T L1 minus E2 T L2. This is equal to 0 because of the conservation property. Now, we have chosen the square or the rectangle in such a way that L1 is equal to L2. From this, you can easily see that the boundary conditions for any medium is that the tangential component of the two electric field must be equal. Because of the conservation of the electric field, this is for any two medium. Okay, so this is one boundary condition. Okay, any question? Now, what did we say? We wanted to know also, if you have a question, please tell me. So this is our goal. Our goal is to see what happens to the electric field component when we reach at the interface between the two mediums. We just found that between the two mediums, the electric field, the component that is tangential, that is along the interface, are equal. Now we want to see what happens to the normal tangent, to the normal. What happens to the normal? What about the normal E1n, E2n? In this case, you can look in the textbook. We will use the Gauss law. Use Gauss law. And if you use Gauss law, you will obtain the second boundary conditions, which is the normal component of the electric flux density of medium 1 minus the normal component of the electric flux density of medium 2 must be equal to the surface charge density. Why? Let me explain here. This is the interface between medium 1 and medium 2. So this is medium 1 that has electric field. and volume charge permittivity of space E1, and permittivity of space permittivity E2, electrical permittivity, right? Now, along the direction, in this direction, the tangential, along the interface, the two electric field components must be equal. However, when we cross normally perpendicular to the surface, we are going from medium 2 to another medium. And when we go from medium 2 to another medium 1, there is a change in the surface charge density. So because of Gauss law and the charge conservation, so we can easily demonstrate it. You can look into the textbook. They use exactly the same treatment as we used for the first boundary condition. And so we have to take into account the fact that there is a surface charge density that has to be taken into account. So those are the two boundary conditions for any two medium. And this is the second boundary condition. Any question? Now, this one, obviously, we know that D in general is equal to epsilon, the electric field. So this also becomes epsilon, epsilon 1, which is the permittivity of dielectric number 1, the normal component of electric field in medium 1, minus the permittivity, electrical permittivity of medium 2, and then the electric field of medium 2, the normal component, is equal to the surface change charge density. Those are the same, just because there is a proportionality factor of this. Okay. So let me just summarize. Let me summarize those boundary conditions that we know. We now know. So the conservative property of electric field. Remember what we have done in chapter 3. We said when an electric field or a vector is conservative, this means that the quantity is equal to 0. And because of the divergence, if you remember the divergence equations, this means that dl is equal to 0. Okay. This gave us equation number 1. Okay. E1 n is equal to E2 n. Okay. This is the first one. And then the second one, using Maxwell's equation, Gauss law, the divergence property of D, which gives us the fact that the normal component of D must change, takes into account the change of the surface charge density when we go from one medium 1 to another medium 2. So this gives us, if you remember, this is Gauss law. And Gauss law is, we can use the Stokes theorem. If you integrate this, so if you remember, the Stokes theorem tells us that if you have if you can integrate over the volume, you can also integrate the integral of the volume is equal to the integral of the surface. Okay, so this gives us the second boundary conditions of the normal component of S. Okay, any question? Now, what we will do? What we have done here is we developed these two. There is a mistake. There is a big mistake here. Who can tell me what is the mistake? Who is following and can tell me what is the mistake?
And the second equation must be the tangential, not the normal.
Exactly. Yes. Exactly. This one, right? Right, chat? Right.
No, the other one. Yeah, that one.
So this one, they are equal. The normal, because you are crossing, right? The normal, you are crossing, you are moving from one, so it's perpendicular to the surface, you are moving from one electric field, one medium to another medium, so you have to take into account surface charge density. But the tangential, no, they are equal. Okay, very good. So now what we will do, we developed those boundary conditions for any two medium. Now we'll just apply them to, for example, dielectric conductor, dielectric conductor, conductor. So now what we will be doing is to apply them to specific materials. Again, let me just copy them so that we don't forget them. So E1T is equal to E2T, okay, and epsilon 1 E1 normal minus epsilon 2 E2 normal is equal to the surface charge density. Okay, this is T. Okay, now let's apply them to the case where I have epsilon 1 is dielectric. Well, the medium 1 is a dielectric, and medium 2 is conductor. Okay, medium 2 is a conductor. Okay. Okay. Now, inside the conductor, what is the electric field inside the conductor? What is the electric field inside the conductor? Zero. Exactly. So the electric field inside the conductor, please, the electric field inside the conductor is zero. I explained it last time. So for medium 2, it is a conductor. This means that the electric field is zero. Okay. If the electric field is zero, this means that E1T is also equal to zero. There is no normal component. Sorry, there is no tangential component. Are you following? Please remember this. There is no tangential component of the electric field when it comes to an interface between the dielectric and the conductor. Now, what about the equation number 2? Equation number 2 tells us that epsilon 1, the normal component, minus epsilon 2, the normal component of 2, is equal to the charge density. But we know that this one is equal to 0 because of the conductor. There is no electric field inside the conductor. So this means that the boundary is epsilon 1 E1N is equal to the surface charge density or the component of the flux. So those are the two boundary conditions in the case of an interface between dielectric and conductor. Let me write it here. Boundary conditions between dielectric and conductor. Okay. Any question? Now let's go to conductor. Let's go to boundary conditions. Conductor. Okay. Now let me also, in fact, here it's a poor conductor. Yeah, it's a poor conductor, not a perfect, not general case, not a perfect conductor. Okay. So here we are talking about, in fact, it's like a general case when we have poor conductor, not a perfect conductor. Yeah, so neither a perfect dielectric nor a perfect conductor. But still I have the this one is not a perfect dielectric, and this one is not a perfect conductor. Okay, we know that E1T is equal to E2T, and we know that epsilon E1N minus epsilon E2N is equal to the surface charge density. Okay. So we know that this is a conductor. Not actually not this is not. This is a general conductor, but not a perfect conductor. Not a perfect conductor. So there is still non-zero electric field inside. It's not a perfect conductor. Okay. So we know that for the current density, current density of medium 1 and the current density of medium 2 is given by this. Okay. So this means if I replace this here, this will give me, so the G1, the tangential coordinate of G1 divided by sigma 1 is equal to the tangential coordinate of 2 divided by sigma 2, the tangent of the current density. So this is, we get it from the first boundary conditions. From the second boundary conditions here, we also can do the following. Epsilon 1, E1n is equal to G1n, the normal component of the current density divided by sigma 1, minus E2, for this one, the normal component G2 divided by is equal to Rho(S). Okay. But here, in electrostatic conditions, there is no charge that is coming from outside. So here we have a G1n and here G2n. So whatever density going from here to here must be the same, because we don't have external charge or a charge that is located in the surface. So G1n must be equal to G2n because of electrostatic condition in a conductor. Electrostatic conditions. This is very important in an interface between two conductors. The normal current density is the same because of why? Because if it changes, well, this means that there is a change in time of the current, which is against the concept of electrostatic condition. That's why these two must be equal to each other. So if this is equal to each other because of the electrostatic condition, then we have the second boundary conditions, which becomes very easy or very simple. G1n, which is equal to G2n, which is equal to multiplied by the permittivity divided by the conductivity of medium 1 minus, and this is equal to. So this is the second boundary conditions for a conductor. Any question? Any question? You can also think about another boundary conditions when you have a dielectric medium 1, dielectric medium 2, and you have E1 and you have E2, and try to calculate the boundary conditions or apply the boundary conditions. Any questions? Any question? Do you have any question? So I will briefly give you some formulas that we have seen already before. The formula of the resistivity, the formula of the capacitance, and the formulas of the electric energy, because electrostatic potential energy, because this we have seen in physics too. I am not going to demonstrate it again. So this will finish chapter 4, and then we can do one or two problems for chapter 4. Okay, so the capacitance. So capacitance is, in fact, what is capacitance? If I take this is a material, a conductor, okay, and this is a dielectric in between. It could be air, it could be, but it is a dielectric that has epsilon here. And so the if I apply a potential difference V, this will create a charge here, positive charge and a negative charge, and of course the electric field is going this way. Now, we know that the electric field let me ask you a question here. Let me ask you a question. This is a capacitor. This is a conductor. This is a conductor. And this is a dielectric. This is a dielectric that has epsilon. What are the boundary conditions here? Okay. What is the tangential electric field at the boundary? And what is the normal at the boundary? Using, remember, E1 tangential is equal to E2 tangential, and E1 normal epsilon 1 minus E1 epsilon 2 E2n is equal to the surface charge density. What about the first equation? Now we'll see if you really understood. Okay? Who can volunteer? What is it? Let's say this is medium number 2, and this is number 1, for example, or the opposite, or this is, yeah, let's take this is medium number 1, and this is medium number 2. This is number 2, and this is number 1. What is the electric field in medium number 1? So I apply a potential difference like here. What is the electric field in medium number 1? 0. Exactly. So medium number 1 is 0. This means that there is no component of the electric field in this direction. There is nothing in this direction. So this means there is only one component that is perpendicular to the surface. Okay, there is one component that is perpendicular to the surface, and this one is 0. This means that the surface charge density, so the E2n is equal to the surface charge density with the minus sign in this sign. So that's why the electric field is going this way, completely perpendicular to the surface between the conductor and the dielectric, because there is no component across or parallel to the surface. Okay. So now let's go back. Now, the capacitance, well, we know that the normal is equal to epsilon. This we have seen in Gauss law. And we also know that so what we can do is the charge is equal to the total charge is equal to the surface charge density times ds, which is also we know that this is equal to epsilon ds, right? And yeah, all what I did is I replaced the surface charge density by its value. Okay. And the total charge is this. We know that the capacitance is equal to Q over potential difference. And we also know that the potential difference is equal to minus if I call this point number 2 and this is point number 1, from minus point number 2 to number 1 of EDL, then I have the definition of the capacitance, which is the integral over the surface of the parallel plate over the surface divided by minus the integral over a line from P2 to P1. This is the general definition of the capacitance. Why we want to do general condition of the capacitance? Because remember, not all electric fields are constant across the surface. And that's why this is a general. But if the electric field is constant, then we go back to this volume, to this simplistic equation. Okay? We have seen that the electric potential energy or electrostatic potential energy. So the electrostatic potential energy is the energy that is stored in a capacitor, for example. And we have seen that it is equal to 1/2 the total charge divided by the capacitance. It is also equal to 1/2 the capacitance times the potential difference across the capacitor. Okay. Any question? So by this, I am done with chapter 4. As you know, chapter 4, honestly, for me, what is new in chapter 4 is just the boundary conditions. It's not because most of things we have seen in chapter 4. So let's give one example before we move. So let's take the flux density of a material is given in a material, or is given by this formula, C cube X in Coulomb per, this is the unit, by the way, in a cube of 2 centimeters side. So in a cube, so you have a cube. So you have a cube, and the flux, electric flux, is equal to this formula. The idea is calculate the volume charge density and calculate the total charge inside. How do you calculate the volume charge density? Any idea? So you are given the flux, electric flux density, and you want to calculate the volume charge density. Now, Gauss' law tells us that the volume charge density is equal to the divergence of vector D, right? And divergence of vector D is the derivative of the components along X plus the derivative of components along Y plus the derivative of component along Z. Okay, are you following? Is this clear? Please don't forget this. Don't forget this kind of equations, because sometimes you will go for the integral, etc. Well, actually, it's not the case. So it's a very easy step. Now, there is no component along Y. There is no component along Z because everything is along X. So what is the component along, what is the derivative is Y cubed, Z cubed. This is the volume charge density. Now, what is the question number? What is the, how do you calculate the charge, the total charge? How do you calculate the total charge? You are given the volume charge density, and you want to calculate the total charge. Hello? Who can volunteer? Can you hear me? Hello? Okay, so now can you hear me? Because I'm confused now. Hello? Okay. Can anyone tell me how can I calculate the volume? I mean, we have the volume charge density, and you want to calculate the total charge. It is a cube, so you have to integrate over x, y, z. You have to integrate this dx, dy, dz. And since the cube is 2 centimeters, you just go from 0 to 2, 0 to 2, 0 to 2. So this will give you 0 to 2 y dy, 0 to 2, well, 0 to 2 dx, and 0 to 2 dz. Okay, and then you can easily see that it is equal to 32 Coulomb. It's a big charge.